Good afternoon, everyone. My name is Ryan Jacob Espitogo, and today we're going to discuss about stacks and queues. So first, before we begin, let us explain what is a stack and a queue. So, a stack is a conceptual structure of elements that follows last in and first out. So for example, we have 1, 2, 3, and 4. And this is our stack. Okay, so since 1 is our last input, this is our last. If deleted, this 1 will also be the first to leave the stack. So that's how stacks work. So now that we're done discussing stacks, we're going to explain what is a queue. So a queue is another conceptual structure of elements that follows first in and first out. So for example, so we first input 1, 2, 3, and 4, and this is our last input. So what happens here? If we are about to delete an element, the first element to be deleted will be 1, since we are following the first in and first out. First in and first out. So this will be the queue. Okay. So the application of stacks and queues can be found in our real life situation. Like for example, we're gonna be using berries as an example, and if we're going to pick the berries one by one, we are going to start with the top first, since it is the last to be inserted in the bowl. And in queues, so an example of a queue is in real life is lining from bus stops. We are not going to insert on the front because we arrive at last. So that's how you define stacks and queues and their real life application. So in our program, we are defining an application of a stack and a queue. So what are those? In our stack, we're using the order tag inventory, and in queues we're going to do an order queue. So what is an order tag inventory? So in our sample program, we are a restaurant. So since we are a restaurant, we have order tags available in the counter, like it's the same with the Chowking and Jollibee na tags, like kanang imong dawaton. And then since order doesn't matter in getting the order tags, because the order tags are based on availability and not the order. And in queues, we are going to follow the order queue, or the order on which the customer arrives and orders their meal. So once they receive the tag given to them by the counter, we are going to assign them to our order queue. So that's how it works. To visualize the real life application, so let's say this is a person and this is our counter. So what happens here? And this is the order tags that we have. So here, so these order tags are gonna be our stack, since it doesn't matter what order we are going to get. For example, someone returned an order tag, and we are going to insert it in the program. And then after the customer orders, it will leave the order tag. It will leave with the order tag and then be processed in a queue line as he waits for his order with the tag on. So he will be the first customer, and this will be second, and this will be third. So in queues, the order does matter. So since customer 1 arrived earlier than customer 2, he will get his order earlier than customer 2 and return the tag back to the counter. So that's how this works visually. So since we're done explaining what stacks and queues are and our potential real-life application, let us now continue with the other functions. So to visualize stack, earlier we have the order tags, diba? So order tags, if returned by the customer after receiving their order, they will go back in the inventory. Basically, this is an inventory of order tags. And if the customer is done ordering, a tag is removed from the inventory. This is remove, this is add. So this is how we visualize it. And so how do we make the tags so how do the tags get added? So let's explain this first. We're going to use a push function. Okay. So here, how does this work? To add something on a stack, we're gonna be using the push function. So in a push function, we're adding something in the stack. So if we have no stacks, for example, this is zero order tags available, and you are going to be adding 1. So to visualize it, we're just gonna be doing this. Let me write it first so that it will be easier. So let's say that we push order tag number 5. So what happens here? If we see it on the push function, it checks if the top is null. Since top is null, we're going to add top. We're going to declare top like this one, and then we will assign pointer to null and then add the value of top. So this is 5. So this is how push works. So what if we say na let's add another number to push, another tag to push. So 7, tag number 7 will simply be added in a temporary linked list. So this is temp, and then temp here, if we see it in this line of code here, temp here connects to our current top, which is 5. So our temp is 7, and it connects to the current top, and then the temp here will be our new top. So this is gonna be our new top. So that's how push works. It's basically like insertion. So in measuring the time complexity, we're going to determine how many steps does it take. So the push function runs on a time complexity of 1. This means that its average, big O and omega notation, only takes 1 step, since we are just inserting 1 element in our current list. And that's how push works. Now, so what if we are going to remove one order tag from the inventory or the counter? So what the function that we're gonna use is gonna be pop. So the function that we're gonna use is gonna be pop. So what pop means is just the deletion of the first element. So that means that 7 here, since it is our latest in the stack, it's gonna be removed first. So what happens here? So what happens here is that it will assign a temporary top. So for example, so this is our temporary top, Gunuhai. Since we copied the value of top. So since this is our temporary top, we're gonna move this from 7 to 5. So our temporary top is now gonna be 5. And then we're going to free top. Since this is our top, this is still our top, huh? Since we are just, so this is our top. Since we are just copying temp top from top, and then we move temp top into 5. So what happens here is we're going to free 7 so that it will be removed from the list. So what happens here is that 7 is gonna be deleted from the list. And then our temporary top will be our new top. And that's how pop works. So same as push, pop actually has a time complexity of 1 also, which means it is only following one step. So that means its theta, big O, and omega notation is 1. So there you have it, an explanation on pop and push, or push and pop. So now we're going to visualize our stacks and queues by running the program. So here, so let's see. Welcome to Poppy's Fun Time ordering system. To start, select one of the options below. Our stack here is choice number 1, which is available order tags. So let's enter that. Use selected available order tags. Counter A, or our current inventory of order tags, currently has 0 order tags available. So let's try to add 1. So we option 1 is gonna be push, and option 2 is gonna be pull. I push, and so option 1 is gonna be push, and option 2 is gonna be pop. So we try to add tag number 5 and tag number 7. So there. After that, we're gonna remove a tag. So what happens here is that it removes the current top, which is 7. So now we have only order 5. So there we go. Also, I forgot to mention, in printing stacks, we're gonna be using an O of n time complexity. So if we say example that in our first run, let's say that we have 5 and 7, diba? As earlier we have that, and also 5. So if this is both our test runs, we're gonna be taking it with n. So since our worst is 2 and our best is 1, the average will be 1.5, or if rounded off, it will be 2 steps. So that's how printing works. It's still the same with the printing queues actually, so I will just discuss that later, but they're still the same. For example, our queue is 5 and 7, and let's say na 5, 7, and 8. So these 3 is our test runs. This is our test runs. what happens here is that it will have a time complexity of maximum 3 steps, which is our worst, and our best would be 1 since that is our first test run, and our theta would be if we average that, it will become 2. So that's how printing works. So I'm just gonna be explaining that first before we proceed. So if we try to visualize it, let's just try stacks. Add counter 5, add counter 7, and add counter 9. If we're going to display that, it's gonna display everything. So our worst time complexity will gonna be 3. Okay, there we go. So after that, we're gonna be explaining queues. So what is queues? So since we mentioned earlier, our queues is gonna be the order our customers claim the order our customers claim their ordered meals, and they're gonna be holding the tags that they have. Since the first person, let's say this is person 1, is this is order tag 60 60, and this is order tag 57, this is order tag 72. So since so this is their order on the way they are entertained in the counter. So this is our visualization. So since 60 is gonna be the first to leave, and 57 is the second and third to leave. So let's say for example 57 and 72 aren't there yet, and we're going to insert person, and we're going to insert the person holding the tag 60. So how do we make that work? Okay, there. So first, let's actually there. So the function that we're gonna use is gonna be enqueue, and this is gonna be tag 60. So we're gonna be using enqueue. So what happens here is just gonna be the same with the stack wherein we add so enqueue. So since we are starting from nothing, and the person holding tag 60 is gonna be the first, so let's just add this one, and let's say this is null. So what happens here is that we're gonna be having rear. So this is gonna be our rear, and our rear is gonna be 60. And since this is our first, our rear will also be our front. So 60 is gonna be also our front, and that's how enqueue works. So if we add persons 57 and 72, it's gonna look like this. So what we're going to do is that we're gonna add or enqueue the person holding tag number 57 since he's the second, and then tags with the tag 72 as the person holding it is in last. So what happens here is that we're going to add 57 to a temporary queue. So this is temp. This is gonna be temp. After we have a temporary queue, it actually points to null. Yeah, it points to null. And this time, our rear and front is not gonna be pointing to null, but rather it's gonna point to our temporary. And that's how that works. And then temporary is gonna be replaced by the rear. So the new rear will be 57. There, the new rear will be 57. And if we are going to follow the process, it's still gonna be the same. In adding 72, we use temporary. temporary linked list or a linked node. And then it's gonna point to null. And then 57 is not gonna, or the second in the queue is not gonna be pointing for null, but rather it's gonna point to 72. And then our new rear will be our current temporary, which means this is gonna be rear. And that's how NQ works. And since we follow the order, so that's how they are inputted in the program. And then what if the person holding tag 60 is now entertained and he received his order? So the tag 60 will be removed. So in removing a queue, in removing an item in the queue, we're gonna be using, so let's say that person 1 holding the tag 60 is now entertained and received his order. So he will be removed from the queue since he's done. So the function that we're gonna be using is gonna be DQ. So how does DQ work? So DQ actually just works like this. What is front is gonna be deleted. So in order to do that, we're gonna be using another temporary node that points to 57. Since this is the next node after 60, and after that we're gonna be removing 60. So since 60 is removed, 57 and 72 are the remaining nodes. Then our temporary will be our new top, or our new front. Our temp is gonna be our new front. So that's how DQ works. And if we're going to go through, like the person holding the tag 57 is gonna be entertained, it will gonna be, and this will be the new front instead. And this is gonna be crashed out, this is crashed out. And that is how this works. And if we proceed further, and this is gonna be removed, what is only left is null. That means there are no people or persons that are currently ordering. So that means that our front, our rear is gonna be pointing to null. So that's how everything works. And now to visualize their time complexities, like stacks, like push and pop, NQ and DQ also follows a time complexity of O1. That means that their best is gonna be 1 step, with their worst is gonna be 1 step, and their omega notation is gonna be 1 step. So if we try to run it, so let's visualize our example earlier. So add order tag to the order queue. So since the order tag 60 came in first, he's gonna be inputted as the first person to receive the order. Next is that order tag 57. So order tag 57 will be the next, and then let's add order tag 72. So that's how the order works. So first is 60, second is 57, and the third is 72. Now that's done, let's actually visualize. If 60 is now entertained, so what happens here is that order 60 receives his order. Then he's gonna be removed from the queue. This means the new first in line is gonna be 57, and that went on until every order is entertained. So after that, after 72 receives his order, order queue will be empty because our front and rear is now pointing in null. So that's how stacks and queues work using our application. And if we're going to print this, it's still gonna be the same as I said earlier with print stack. it's gonna print this one first, then this one, and then this one. Let's say that wala pa na to. Let's say that we have not yet dequeued it. So it's gonna be printing first isa 60 57 72. So in this we're gonna display. So what happens here is that we are printing 60 first. After that we're gonna print 57, and after that we're gonna print 72, and that follows a time complexity of O(n) because it follows a loop. So for example, in this one our time complexity is 3 steps. That means that our let's say that we have test runs. Yeah, we have test runs. So we first inputted 60, diba? And then we input 57. So this means it's 60 and 57. And then we input 72. So this means 60, 57, and 72. So that means that in our test runs, we have the best case scenario of 1. And then the worst of 3. And then the theta of 1, 2, and 3. And our average is gonna be 2. And so that's how the time complexities of both print Q and print stack. So that's how they work. So now that we explained everything from the stacks and queues and their sample demonstration, we can now conclude this discussion. Thank you for listening, everyone, and I hope you understand something in this video, and I wish you the very best in life. Thank you for listening. Goodbye.